Aluminum conductor cable offers several advantages, primarily cost savings. Aluminum is significantly cheaper than copper, making it an attractive option. Another advantage is weight. Aluminum is lighter than copper, reducing the overall weight of the wiring system. Furthermore, aluminum is naturally corrosion resistant, making it suitable for outdoor applications. Aluminum conductor cable can carry a similar current as copper cable, but it requires larger diameters due to its lower conductivity. However, there are also disadvantages to consider. Aluminum is a less efficient conductor of electricity than copper, which necessitates larger conductor sizes to achieve the same current capacity. Aluminum also has less tensile strength than copper, requiring additional supports or larger cable diameters for mechanical strength. Aluminum expands and contracts more than copper with temperature changes, potentially leading to connection loosening or stress on components. Aluminum requires special joint preparation techniques and tools to ensure reliable connections and prevent oxidation. Aluminum conductor cable exhibits a higher voltage drop than copper, which may be a significant concern in some applications. Comparing costs, aluminum conductor cable is typically 30 to 50% less expensive than copper cable for the same ampacity. However, the larger conductor size and the need for additional support may partially offset these initial cost savings. Aluminum conductor cable is most suitable for applications where firstly, cost is the primary concern, secondly, weight reduction is important, thirdly, corrosion resistance is desired, fourthly, voltage drop is not a critical factor, and fifthly, adequate support can be provided to accommodate the larger cable diameters. On the other hand, aluminum conductor cable may not be appropriate for applications where firstly, high conductivity is essential, secondly, tensile strength is crucial, thirdly, space constraints are a concern, fourthly, voltage drop needs to be minimized, and fifthly, connections are frequently made or modified. In conclusion, aluminum conductor cable can be a cost-effective alternative to copper conductor cable in specific applications. However, a careful evaluation of its advantages and disadvantages is essential before specifying aluminum conductor cable. Consulting with a qualified electrical engineer is highly recommended to determine the suitability of aluminum conductor cable for specific projects and to ensure compliance with all applicable codes and standards. When considering the ampacity of aluminum conductors, it's crucial to consult the National Electrical Code, specifically Table 310.15b16, formerly Table 310.16, for allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius to 90 degrees Celsius, not more than 3 current carrying conductors in a raceway or cable or earth, based on ambient temperature of 30 degrees Celsius. Adjustments must be made for ambient temperatures other than 30 degrees Celsius as outlined in Table 310.15b2. Additionally, when more than 3 current carrying conductors are in a raceway or cable, the allowable ampacity must be reduced as per Table 310.15 colon. For an 800 amps application, you will likely need multiple parallel runs of aluminum conductors, as single conductors may not be available to carry that much current while remaining within the NEC ampacity limits. The specific size and number of conductors depend on the insulation type, ambient temperature, and the number of conductors in the raceway. For example, if you were using type THHN aluminum conductors rated for 75 degrees Celsius in an ambient temperature of 30 degrees Celsius and with not more than 3 current carrying conductors in a raceway, you would need to refer to the 75 degrees Celsius column in Table 310.15b16. You would find that a single 750 kcmil aluminum conductor is rated for 475 amps. Therefore, you would need at least 2 parallel runs of 750 kcmil aluminum conductors per phase to carry 800 amps. Note that the 750 kcmil size is also written as 750 cm depending on the literature. However, remember that this is a simplified example, and you must account for all applicable correction and adjustment factors as well as ensure proper termination and support of the conductors. Also, you need to ensure that your overcurrent protection device is sized correctly to protect the conductors according to NEC Section 240.4. The higher voltage drop associated with aluminum conductors should be carefully considered. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can lead to reduced performance of equipment, such as motors running slower or lights dimming. The NEC recommends that voltage drop should not exceed 5% for feeders and branch circuits combined. For feeders, the recommended maximum voltage drop is 3%, and for branch circuits, it is 2%. The voltage drop can be calculated using the following formula: voltage drop equals current times resistance times length, all divided by 1000, where current is the current in amps, resistance is the resistance of the conductor in ohms per 1000 feet, and length is the one-way length of the conductor in feet. Because aluminum has a higher resistance than copper, the voltage drop will be greater for a given current and conductor size. Therefore, you may need to increase the size of the aluminum conductors to achieve the same voltage drop as copper conductors. Proper termination of aluminum conductors is essential to prevent oxidation and ensure reliable connections. Aluminum readily oxidizes when exposed to air, and this oxide layer can increase the resistance of the connection and lead to overheating and failure. To prevent oxidation, you must use connectors that are specifically listed and labeled for use with aluminum conductors. These connectors are typically made of aluminum or are plated with tin or nickel to provide a corrosion-resistant surface. Before making the connection, the aluminum conductor should be cleaned with a wire brush and coated with an oxide-inhibiting compound. This compound helps to break down any existing oxide layer and prevent further oxidation. The connector should be torqued to the manufacturer's specifications using a calibrated torque wrench. Over-torquing can damage the connector, while under-torquing can lead to loose connection and overheating. Regular inspection and maintenance of aluminum connections are essential to ensure their long-term reliability. Connections should be inspected for signs of overheating, corrosion, or loosening. If any problems are found, the connection should be cleaned, retorqued, or replaced as needed. When considering the use of aluminum conductors, it is also important to be aware of the different alloy types available. The most common alloy used for electrical conductors is 1350 aluminum, which has a conductivity of approximately 61% of copper. However, other alloys are available with higher strength and improved corrosion resistance. For example, Amanus 8000 series aluminum alloys are often used for building wire. These alloys have higher strength and better creep resistance than 1350 aluminum, making them suitable for use in connections that are subject to mechanical stress. The choice of alloy will depend on the specific application and the required performance characteristics. It is important to consult with an electrical engineer and the conductor manufacturer to select the appropriate alloy for your needs. In summary, specifying aluminum conductor cable requires careful consideration of several factors, including ampacity, voltage drop, termination methods, and alloy type. Consulting with a qualified electrical engineer is essential to ensure that the installation meets all applicable codes and standards and that the aluminum conductors will provide reliable performance over the long term. The National Electrical Code provides detailed requirements for the installation of aluminum conductors, including conductor sizing, ampacity correction and adjustment factors, termination methods, and overcurrent protection. Always refer to the latest edition of the NEC for the most up-to-date information. Aluminum conductors are often used in large-scale applications such as service entrance conductors for buildings, feeders for distribution panels, and branch circuits for lighting and receptacles. They are also commonly used in underground installations where their corrosion resistance is an advantage. When used in service entrance conductors, aluminum conductors must be sized according to the requirements of NEC section 230.42. The ampacity of the service entrance conductors must be not less than the calculated load as determined by Part 3, Part 4, and Part 5 of Article 220. When used in feeders, aluminum conductors must be sized according to the requirements of NEC section 215.2. The ampacity of the feeder conductors must be not less than 125% of the continuous load plus 100% of the non-continuous load. When used in branch circuits, aluminum conductors must be sized according to the requirements of NEC section 210.19. The ampacity of the branch circuit conductors must be not less than the rating of the overcurrent device protecting the circuit. In addition to the sizing requirements, the NEC also specifies requirements for the installation of aluminum conductors. These requirements cover topics such as conductor support, termination methods, and protection against physical damage. Aluminum conductors must be supported in accordance with NEC section 314.23. Conductors must be securely fastened in place and must not be subjected to excessive strain. Aluminum conductors must be terminated in accordance with NEC section 110.14. Terminations must be made with connectors that are listed and labeled for use with aluminum conductors and must be torqued to the manufacturer's specifications. Aluminum conductors must be protected against physical damage in accordance with NEC section 300.4. Conductors must be installed in raceways or protected by other means to prevent damage from abrasion, impact, or other sources. When designing an electrical system using aluminum conductors, it is important to consider all of these requirements to ensure a safe and reliable installation. Always consult with a qualified electrical engineer and refer to the latest edition of the NEC for the most up-to-date information. Remember also to consider the environmental conditions in which the conductors will be installed. Factors such as temperature, humidity, and exposure to corrosive substances can affect the performance and lifespan of aluminum conductors. For example, in coastal areas where there is a high concentration of salt in the air, aluminum conductors may be more susceptible to corrosion. In these environments, it may be necessary to use special corrosion-resistant alloys or to provide additional protection for the conductors. Similarly, in high-temperature environments, the ampacity of aluminum conductors may need to be derated to prevent overheating. The NEC provides ampacity correction factors for different ambient temperatures. Proper grounding and bonding are also essential for electrical safety when using aluminum conductors. The grounding system must be designed to provide a low impedance path for fault current to return to the source, which helps to trip overcurrent devices and prevent electric shock. The bonding system must be designed to connect all metal parts of the electrical system together to create an equipotential plane. This helps to minimize the risk of electric shock by ensuring that all metal parts are at the same voltage potential. The NEC provides detailed requirements for grounding and bonding in Article 250. It is important to follow these requirements carefully to ensure a safe and reliable electrical system. Also, always consider the long-term maintenance requirements when specifying aluminum conductors. Regular inspection and maintenance are essential to ensure that the conductors and connections remain in good condition and that any potential problems are identified and addressed promptly. Inspections should include checking for signs of corrosion, overheating, or loose connections. Connections should be retorqued periodically to ensure that they are tight and secure. Any damaged or corroded conductors or connectors should be replaced immediately. By following these guidelines, you can ensure that aluminum conductors provide a safe, reliable, and cost-effective solution for your electrical needs. Remember to always consult with a qualified electrical engineer and to follow all applicable codes and standards.